three-phase induction motor. So objectives are explain the diagrams how an induction motor is treated as generalized transformer. Draw equivalent circuits of for three-phase induction motor. Introduction. The transformer works on the basic principle Faraday's law of electromagnetic induction. Similarly, the three-phase induction motor also works on the principle of electromagnetic induction. It is a transformation. Its rotor winding receives energy from stator by means of induction, like transformer action. The following diagram shows the construction of a three-phase induction motor. This is the diagram. The rotor windings of three-phase induction motor receives energy from stator by means of induction. Therefore, its stator winding is directly connected to AC supply. The three-phase induction motor is a singly excited machine. It does not require any excitation. An induction motor is treated as generalized transformer. It is possible to compare the operation of induction motor to that of transformer. The stator and rotor of an induction motor can be compared to primary and secondary of transformer. The transformer here, see in this motor, transfer of energy from stator to rotor of an induction motor takes place by induction. It is entirely inductively by the flux linking between stator and rotor. In transformer, the frequency of induced EMF and current in primary and secondary is always same. However, in the induction motor, frequency of stator EMF and current on the stator side remains same but not on rotor side. Frequency of rotor EMF and current depends on the some here the slip. Second one is load on the motor. The slip is the difference between the synchronous speed and actual speed of the motor. It is expressed as a fraction of synchronous speed. S is equal to ns minus n by ns. At starting, the slip of the induction motor S is equal to 1. The frequency of the supply of the stator and of induced EMF in the rotor is same. In the case of transformer, the entire energy present in its secondary circuit is in the electrical form, but here in induction motor, part of its energy in the rotor circuit is in electrical form and the remaining part is converted into mechanical form. In general, an induction motor can be treated as a generalized transformer and it satisfies though through the following relations. If supply is given to stator three-phase induction motor, a rotating field is set up and EMFs are induced in stator. E1 is the stator induced EMF and it is rotor induced EMF. E1 is equal to 4.44 kilowatts F1 N1 pi 1. E2 is equal to 4.44 kilowatts F2 N2 pi 2. Here Kw1 and Kw2 are winding factors for stators and rotor windings respectively. E1 by E2 is equal to Kw1 N1 by Kw2 N2. This expression is similar to the voltage transformation. The ratio E1 by E2 is equal to N1 by N2 of the transformer. This is called transformation ratio. There is slight difference in the above equations. The use of distributed winding for the induction motors as compared to the concentrated coils used in the transformer. An induction motor at standard still exhibits the same characteristics of a transformer on no load. In induction motor also the leakage fluxes as in transformer. Therefore, the operation of both the devices is similar even under load conditions. The stator and rotor have winding resistance and leakage reactances as in transformer windings. A transformer under short circuit is similar to an induction motor with blacked rotor. However, some differences are there in between two. serial number, transformer, induction motor. Number 1, what is that? It is a static device. There is no rotating part in a transformer. Here, induction motor is rotating device. And second one is the transformer has concentrated coils and here the distributed winding is used. For third one is for the transformer magnetizing current is very less. Here magnetizing current high due to air gap between the stator and rotor. For the air gap, it taking the more magnetizing current. Next one, efficiency is high and losses are low in transformer. In induction motor, so low efficiency due to high losses. Here in induction motor, mechanical losses are also considered. Those are the windage and friction losses. Here in transformer, there is no windage and friction losses. Here, an equivalent circuit of an induction motor. It is possible to compare the operation of induction motor that of a transformer with equivalent circuit. The energy is transferred from stator to rotor is same as in transformer operation. Equivalent circuit enables the performance characteristics of the induction motor and all for phase quantities are used. It is clearly showing the following circuits. See, observe this one. So here, see this one. Here, this one. Here, stator and rotor is given. At stator side, the supply voltage is V1, current I1. V1 supply voltage, current is I1. R1, X1. So R0 and X0. This I0 current is divided into IW and IMI component. This is the working component of current and IMU is the magnetizing component of current. Here the induced EMF stator is E1. E1 at stator side is E1. Now the rotor side, the resistance and R2 and the reactance is SX2 and the voltage is here SX2, SE2 at rotor side induced EMF on in running conditions. Now the same diagram equivalent circuit can be represented. So they given in below figure B, equivalent circuit B. So this is here This is replaced here. This stator rotor is replaced with here. V1, I1, R1, X1, R0, X0, IW, I mu, I naught. Here stator turns number of turns N1 this one, and induced EMF is E1, and here the rotor side EMF induced is E2, number of turns N2, the resistance is R2, and reactance is SX2. This is the actual rotor side. Here at rotor side circuit, S into E2, current is I2 R2, current is I2, resistance is R2, and the reactance is SX2. So here generally SX2 is the varying quantity, but in equivalent rotor circuit B, here by dividing in this circuit, we are dividing here divided by S, here divided by S, here divided by S, here divided by S. So here S cancelled, here R2 by S, and here also S by S cancelled. The remaining is here. IC2 by S is E2, R2 by S is R2 by S, SX2 by S is X2. So this is the equivalent rotor circuit. At rotor side. Following are the parameters of the equivalent circuit. R1, X1 stator winding resistance and leakage reactance. R2, X2 rotor winding resistance and leakage reactances. At standard cell. SX2 is the rotor leakage reactance at slip under running condition. R0 is no load branch resistance and it carries working component of current. IW of no load current of I0. X0 is no load branch reactance and it carries magnetizing component I mu. E1 and E2 stator induced EMF and rotor induced EMF at slip S. Now the rotor input comma P2 is the sum of rotor copper losses PC and the mechanical power developed PM. It is possible to represent the electrical equivalent of a mechanical power developed as follows, that is P2 is equal to PC plus PM. A summary, we have discussed the following induction motor behavior compared to with in transformer action, and difference between induction motor and transformer. The performance characteristics of induction motor is enabled by equivalent circuit. This is the